Hi everyone, my name is Sophia Pedigo, and today we're going to be looking at the second half of a problem that I started going over in my last video. So more specifically, we looked at a situation in which we have two spherical tanks. These spherical tanks have an initial steady state height h1, and the second tank has an initial steady state height of h2. We've got a radius 1, a radius 2, and we've got some cross-sectional area for this pipe that connects the two tanks called A12, and we have some cross-sectional area here that's A2. Now, we also have this flow rate going into the first spherical tank, which we called Q1 in, and we have a flow rate going into the second spherical tank called Q2 in. Now, in my last video, we were also able to derive a couple of equations that allowed us to find the flow rate Q12, the flow rate going between these two tanks, and the flow rate Q2 for the fluid that's leaving the second tank. After we found that, what we did is we actually found the differential change in volume with respect to time, and then we divided that by the cross-sectional area of the spherical tank in order to get the differential change in height with respect to time. So using all of this information, now what we're going to do is we're going to look at this problem for a second time, this time looking at it through Google Colaboratory. And we've also been given some additional information here where we've got some values for these variables like the radius, the cross-sectional area. We've been given the initial steady state heights for these spherical tanks, and we've also been told that at time equal to 100 seconds, tank 1 is reduced by 80%, the flow of tank 1 is reduced by 80%, I should say the flow rate going into tank 1, and at time equal to 200 seconds, the flow rate going into tank 2 is increased by 250%. So, with all this information, what we want to do is go in and solve for the initial flow rates with those initial steady state times. I don't know why this isn't working. Is it working now? Okay, hopefully that works. We want to go in using this information, solve for the initial flow rates. I don't know why this isn't working. You know what? We're just going to do this. Woo! Boy! Come on. Might as well use this time to explain what I'm doing. For some reason this isn't working, so we're going to see if this does, which apparently it is. I don't know why it's not, but this is... Okay. This is just some information that I've imported so we can solve that initial value problem that I've got, the differential change in height with respect to time. Imported Jack's Numpy, Jack's Plotly, so we can make some nice subplots. And now what I'm going to do is just go ahead and define these variables that we've been given. So the radius for both of the tanks, we've got the cross-sectional area for the pipe that connects the tanks, and that happens to be the same for both A12 and A2. And then we've got the initial height, which I want to be very careful to define as H1 initial, just because when we go and solve for the change in heights with different times, we don't want to get that confused with the initial height values that we've been given. So, and then we're also going to go ahead and just define the acceleration due to gravity, because no one wants to deal with that, typing that in multiple times. So, now that we've got all that information in, basically what we're going to just be doing is putting in those equations that I solved for in my previous video. So, we had Q1 in, Q12 initial. Again, it's kind of important that we make sure that we're differentiating between the initial flow, the steady state flow, and then later when we solve for those flows at different times, we're just going to call it Q12 so we don't get it confused. And that was just equal to the cross-sectional area multiplied by the velocity, And I'm taking the sine of this height difference, and I talked about this a little bit in my previous video. The reason we're doing that is because we're also taking the square root of the height difference, and we don't know that that difference is always going to be positive. So we can't take the square root of a negative number. So we're accounting for the sine of that value outside of the square root, just so that doesn't cause any problems. Again, taking square root of negative number doesn't really work, at least in this case. So then we've got the Q2 initial, and that was just equal to the cross-sectional area of the pipe multiplied by the square root of 2 times the acceleration due to gravity multiplied by H2 initial. Now, we're solving for the initial flow rates with the initial heights and initial values that we've been given, right? So what we're going to do is we're going to make a little easy assumption just so we can get those values. And we're going to say that the flow rate going in the Q1N initial is going to be equal to Q12 initial. So it's a steady state, so it's going to be equal. The amount going in is going to be equal to the amount leaving. The flow of the liquid in equals the flow of the liquid out. So we've got Q1 in is equal to Q12 initial. And then we've got Q2 in initial is equal to Q2, the stuff going in minus the stuff leaving. Is that right? Yeah. Okay. Okie dokie. Now that we've got that information, I talked about how we were able to get the differential change in height with respect to time by dividing the differential change in volume of the spherical tank with respect to time. So let's go ahead and define that cross-sectional area of the tank so that we can actually use that easily and just plug it into some of the other equations that we're going to be using. And this is something that I solved for in my previous video, and it is just going to be equal to pi multiplied by the radius squared minus the radius minus h and that quantity squared. Okay, now we've got all these bits and pieces. We've essentially solved for the flow rates using the initial flow rates using the initial heights that we've been given. And now we're going to go in and we're going to use that equation, that differential equation that we were able to solve for in my first video, and we're going to use that to kind of create a model and look at the change in heights of these tanks as the flow rate changes. Like we said up here, we're going to end up reducing the tank 1's flow rate by 80%, and tank 2 is going to be increased by 250%. And we're going to look at all of those changes that happen with respect to time. So let's go ahead and define that equation that I derived. So we're going to call it dH dt, this function that we're working with. It's going to take in time and height. And we're also going to be sticking this into an array. So we want to define which element of the array that we're working with. It's important to note that Python indexing starts at 0. So we're going to say our first element, h1, we're going to say that that's h, and that's going to be the first element of the array, so 0. And then our height of tank 2 is going to be equal to the second value in our array. So now that we've got that, like I said a little bit earlier, up here we've got Q, the flow rate 1, 2, the flow rate from tank 1 to tank 2 initially. Now what we're going to do is we're going to look at that as it varies with time. So we're going to just have Q12, we're no longer looking at the initial flow rate, and that's going to be equal to A12, cross-sectional area doesn't change. We're going to have the sine this time of just h1 minus h2. No longer looking at the initial heights, we're looking just at any height now. And And we're going to take the square root of 2 multiplied by g multiplied by the absolute value, of h1 minus h2. Okay, then we're going to do the same thing for the flow rate that's leaving tank 2. We're going to define this again, so it's no longer taking into consideration the initial values for the height, but any values for height. So cross-sectional area stays the same. This time we're going to have the square root of 2 times acceleration due to gravity multiplied by h2 at any time. And this is going to return to us a nice little array, and it's going to have this. So what's in this array is basically going to be that differential equation that I showed you at the beginning of this video, where it's essentially the change in volume, basically, of the tank divided by the change in height. So looking at that, it's going to be Q1, the flow rate in to the tank, minus the flow rate leaving that tank initially. So it's going to be Q minus Q12. I'm going to put parentheses around that. We're going to divide that by the cross-sectional area. And again, that's taking in the height and the radius. And then for the second tank, we're going to say that that is equal to, let me put a parentheses there, that's going to be equal to Q2N, the flow rate going into that second tank, plus the flow rate Q12, we're assuming that that's flowing into that second tank, minus Q2, the flow rate leaving that tank. And then we're going to divide that by the cross-sectional area that we derived. Okay. Now, let's see if that works. Yes, it does. So far, our life has been pretty easy. We've basically just thrown those equations in that I derived in that previous video, and this part sure was kind of messy. You're sticking something into an array, that's never fun. But we haven't really looked at time yet, and that's a pretty important part of the problem statement that we're given, because we're specifically looking at a time equal to 100 seconds and a time equal to 200 seconds. So this is where it gets a little bit messier, but it's not bad. I'm going to show you basically sigmoid function. Ugh. Well, it still came up. Oops. Basically, what we're going to be looking at is we want to see what happens at these specific times and at these specific changes in flow rate. And the way that we're going to do that is by using a sigmoid function. And these guys are pretty useful because it's basically like you're flipping a switch and you can look at... Why is this not working? Okay, well, you saw the basic principle of what the sigmoid function looked like. And what's nice about that is we can use that to look at a specific time in a time frame, I guess, might be easier to say, in which this change is occurring or this change is happening. So we can use it to specifically look at 100 seconds, and we can use a specific scale so we can take into account that tank 1's flow rate is being reduced by 80% and that tank 2's flow rate is being increased by 250%. So with this in mind, basically what we're going to do is we're going to go ahead and define, I don't know if it's working. There it is. There's our nice little sigmoid function. We're basically going to be using this to look specifically at what happens at 100 seconds and what happens at 200 seconds. And so what I'm going to do now is I'm just going to go in and I'm going to define this sigmoid function, which we're going to call switch. And its inputs are going to be the time. It's going to be V1, V2, so, and then the time that the switch happens, and then the scale. And actually, I also want to go ahead and put in a time frame. So like, we're going to go ahead and look for when we create the graph for this specifically. We're going to look at all the way out to 500 seconds. Where did this go? There it is. Okay. So this is going to return our sigmoid function that I just showed you. This is literally right over here. And we're going to say that it's the time minus the time of the switch divided by our scale. And we're going to multiply that by our flow rate, so V2 minus V1 plus V1. Okay. Let's see if that works. Yay. How do I add code? There we go. Next, what we're going to do is we're going to define. So what we have down here is we have the flow rate going in, but basically what we're going to do now is we're going to take into account the time, because right here, Q1N initial, obviously that's the initial one, but what we're doing now is we're kind of altering that equation just a little bit so we can account for different time changes, and we're doing that using the sigmoid function. So we're going to say that our Q1N with change in time accounted for, so Q1N is going to return the switch that we just defined, that function that we just defined, and it's going to have an input of time. It's going to have Q1N initial, and our V1 is going to be equal to the change in flow rate initial. Did I do that wrong? No, okay, sorry. Our V1, our initial, that's going to be like our velocity going in, and then our velocity that changes is going to be equal to, it's going to be reduced by 80%. So we're going to say that that is going to be equal to Q1N initial multiplied by 0.8. And then the time that this happens at is at 100 seconds. And our scale, we're going to say, is 1. And then we're going to do the same exact thing for our Q2, because we're also told that the flow rate Q2 going into tank 2 at 200 seconds increases by 250%. So we're basically doing the same thing for that flow rate. So we're going to define Q2, and that's going to, we're going to return the switch function, and it's going to be our time, and we're going to have the V initial, which is our like initial flow rate, so that's just Q2 in initial. And then we're saying what happens, our V2, what happens to it is that it's increased by 250%. So we say that that's Q2 in initial multiplied by 2.5 for the 200%. And this happens, the time of the switch happens at 200 seconds, and our scale is 1. So let's see how that works. Okay, so that's good. Now what we want to do is we've basically solved for our initial flow rates, and we've got all this good fun information for our differential equation. We've accounted for the fact that this flow rate is changing at 100 seconds for tank 1 and it's changing at 200 seconds for tank 2. And now we're going to see if we can actually solve this initial value problem. So let's go ahead and do that. I'm going to scroll down a bit. Okay. We're going to say we're going to solve our initial value problem finally. And we've got some inputs, so this kind of tells you all the good fun information up here for initial value problems. We need our function. Our function is dh dt, and we're going to have our time span. So right up here, I said that our end time span is 500 seconds. So we're going to say that our time span starts at 0 and it's going to go to t end, which is 500 seconds. And then the next part of this, if it pops up, maybe it will. Yeah, there it is. Our initial values for y, and that's just going to be our heights that we have. So it's h1 initial and it's h2 initial. And then we're going to have, if it pops up here, nice, we're going to have our methods. So that's RK45. There are different methods that you can use to solve initial value problems. We're going to use a method called Radu. Yeah, there we go. And our dense output equals true. Let's see if this works. I don't think I did that. Let's go all the way down. Moment of truth. It's thinking about it. Oh, it worked. Yay. Okay. Now that we've got that done, we've got all the bits and pieces are coming together here. But, you know, we could, you know, look at this just numerically and see what values that we're given. But, you know, graphs are kind of a nice way to look at information. So that's what we're going to do. So we're going to set up our time plot, okay? So that's just going to be equal to, we're going to create, we're going to use linspace. To basically, what that does is it just gives us a bunch of different values. So we're going to start at 0. We're going to end at t equals to end and t end for 500. And because we're starting at 0 and we want 500 points, we're going to end up with 501. So that's our time plot. And then we're going to say, we're going to put our solution into here. So okay, so far so good. Let's see if we can keep up the good work. So we're going to make our figure now. And we're going to say that it has one row, rows equal to 1, and we're going to say the columns are equal to 2, because we want to look at not just the heights, but also the flow rates. So we're going to have our heights in one column and our heights in the other column. So that'll be nice. And we'll be able to see that. Okay, cool. That's working. Then we're going to add stuff to our figure. Up here, if I can scroll, let's see. Up here, I imported graph objects as GO, so we're going to just use that to go ahead and select our scatter plot. And we're going to say that our x is equal to our time plot that we set up. So those are going to be all of our x values. And our y values are going to be equal to our solution. And we're looking at our first height. So that's going to be the first element in our array. So 0. And we're going to name this height 1. Yep. And we're going to say that we're going to put this in row 1. Oops. Row 1. Columns 1. See if that works. Nope. I think I just spelled that wrong. Wait. Ah. Whoa! Okay. Let's see. Let's go ahead and do the other one. So this time we'll be looking at the second element in our array, and this is going to be height 2. Here we go. I don't know. This kind of looks funky. Huh. Well, I'm gonna throw the yeah, well, actually let's just do it this way. Don't need to type more than I already have. Oop. We're gonna say that our y values this time. This time we're gonna graph the flow rate. I'm not sure. I think it looks kind of funky. I could be wrong. But I want to graph this, and if the flow rates look weird, then I'll look back and see if it is weird. And this is going to go into column 2. This is Q2. And this is Q2N, and this is going to go into column 2. Okay. There we go. So we were able to take those equations that we derived in my first video. We were able to basically solve for, well, first off, we started putting all of our variables in. We put in our initial flow rates, and we were able to solve for the initial flow rates. We were also able to define the cross-sectional area and our differential equations, and then we went back and we accounted for the change in time using the sigmoid function. So we were able to define our sigmoid function and use it to adjust for the time and the flow rate changes, so that reduction in flow rate and increase in flow rate. And then we were able to use all of that to create plots that showed us the change in our heights for tank 1 and tank 2, and the change in our flow rates for tank 1 and tank 2. So that's all I have for this video, and I'll be back with more.